Good morning, everybody. I'd like to welcome you to the Low Carbon Vehicle Partnership and the APC's webinar series on automotive life cycle analysis. My name is Gloria Esposito and I'm Head of Projects at the Low Carbon Vehicle Partnership. I'm moderating today's session with my colleague Philippa Olden from the APC. The theme of today's webinar is closing the end-of-life loop for electric vehicles. And we're going to be exploring how to reduce the environmental burden at the end of life, looking at recycling and reuse of critical metals in components such as batteries and magnets. I'm very delighted to have a range of expert speakers today. Those include Professor Alan Walton from the University of Birmingham, Jackie Murray from the Faraday Challenge, Professor Francis Wall from Exeter University, and Professor Emma Kedrick from the University of Birmingham.
Thanks, Gloria. So good morning, everybody. Welcome back to some of you, and thanks for joining us. For those of you which this is your first session. So as with all events, we like to do a little bit of housekeeping. So if I just start by sharing my screen, you'll be able to see this hopefully. So we encourage you to pose your questions to the panelists. Please use the Q&A box at the bottom of your screen. We also recommend that you try and start some chat going in the chat section. You can either choose to chat directly with the panelists or with all attendees. So feel free to start discussions or debates in there. We will be recording today's session, so the presentations will be available after this, along with the speakers' bios. In addition to that, we sometimes don't get round to answering all the questions, so we'll be including those answers once those recordings have been made live. We encourage you to be social, so please use the social media channels using a hashtag LCA week. With those, we will follow up with you, and it will also be able to see other attendees and the speakers who's interested in the topic and maybe contact you post the event. At the end of the session, we'll be doing a short survey, which will take about 2 minutes, and that is to gather your feedback on what you thought of the session and the speakers, but also looking at future events. So that's it from me, and now back to Gloria.
Thanks, Philippa. I'm delighted to introduce our keynote speaker today. That's Professor Alan Walton. He's Professor of Critical and Magnetic Materials and Co-Director of Birmingham Centre for Strategic Elements and Critical Materials. Alan, over to you for your presentation, please.
Thank you, Gloria. I'll just share the screen. My talk today is on recycling of end-of-life magnets and applications. I'm from the University of Birmingham, but I have to declare that I'm also the director of a company called Hypromag, and if I have time, I'll touch upon that at the end of this presentation. So I run the Magnetic Material Group at the University of Birmingham. They're really the only group in the UK that looks at processing of permanent magnets. So just firstly, for those that aren't aware, a rare earth magnet is actually a family of materials. Firstly, based either on samarium cobalt, which tends to be used in the aerospace industry, or neodymium iron boron, which is about 95% of the market overall. And the thing to be aware of is that neodymium iron boron magnets can be made in different ways. You can mix it with a polymer, form an injection bonded magnet using 2 different feedstocks, either melt spun ribbons or HDDR powder. You can sinter the materials, which is the majority of the market dominated by Chinese companies, or you can use a die upset and forging method to form a fully dense magnet using a completely different route. So there are different ways of making those materials. So what are they used for? Well, they're used in a very wide range of applications, and actually the recycling market will be dominated by applications outside of automotive to start with. So they're used in offshore wind turbines, up to around 5 tons of material used in those applications. They're used in the automotive sector for generators, motors, loudspeakers, power steering, fans, and so on and so on. They're used in the drive motors of electric bikes. They're used in electronics, so things like hard disk drives, and they're prevalent in things like mobile phones. And I'll go on to some of the challenges of those sectors a little bit later. So if you're going to make a magnet, if you go from mine to magnet, you go through multiple processes. So you dig the material out the ground, you crush up the rocks, you chemically leach them out, forming chlorides, you separate them chemically to oxides. You then electrowin, similar to aluminium, to get to a rare earth metal. That rare earth metal is then cast into an alloy and it's fed into the magnet manufacturers, which I'll cover in the next slide. And then eventually it's cut and shaped. And actually a lot of the cost and the energy and the environmental footprint is in these early steps at the top of this diagram up here. Where we come in my group is we go from cast alloy through to magnet manufacture, and we have pilot scale casting systems and magnet manufacturing on site at the university. Now, the thing to appreciate is the cost of manufacture is dependent on many things: the type of ore, the processing you have, composition of magnet you want to create, the size of the magnet, and the complexity of the shape. All of that changes the ultimate cost of the magnet at the end. So once you have a cast alloy, and the alloy is cast either into book molds or by a process called strip casting, then the most conventional way of making a magnet is to crush and process that material using hydrogen, which I'll show you later, into a powder. That's produced by jet milling, and then the material is blended and then pressed and sintered at high temperature in vacuum. And the thing to appreciate is all that processing is done inertly in glove boxes, which is one of the reasons why the processing can be expensive. So the main topic of this talk today is on recycling. Why recycle rare earth magnets? Well, we import far more material than we manufacture in the EU, about 10 times. If short loop recycling, which I'll cover in this talk today, could be achieved, then the economics become much more favourable. The environmental footprint of those routes will be far smaller than primary production of NdFeB. It would provide a secure supply of material for the EU, and there's significant pressure from China. It would help with the balance problem. Frances Wall is talking after me, and I'm sure she'll talk about the breadth of elements you find in a mine source of material. But essentially, if you dig rare earths out of the ground, you have all of them mixed together. You only actually need 3 or 4 in a rare earth magnet. So you have to deal with all the other elements that you potentially can't sell, which is called the balance problem. And the cost of building a recycling plant could be a fraction of that required for primary production. But again, it depends on the route that you take. But there are significant problems for recycling. And for quite a bit of the talk today, I'm going to talk about the problems that we have in recycling and how the end user industries could help with that. So firstly, how do you know that there's an NdFeB magnet in your product? If you took 10 handheld drills, separated the magnets from them, about half of them would be neodymium iron boron and the rest would be ferrites. So how do you detect which magnets are in there? The magnets are often very small. So mobile phone magnets can be less than 300 milligrams. The composition of the magnets is changing, and I'm going to describe why that's a problem later. The final magnets are typically coated and have a higher oxygen content. That causes a problem for reprocessing. The magnets are often, magnetized, and shredding causes you a problem. The products are not designed for disassembly. They're not labeled at present, but that is changing for some companies, and the economics are quite challenging. The other issue is actually getting the supply chain up and running in an immature market. And again, I've put some points at the end of this presentation. And the thing to appreciate is that a large majority of the cost for recycling is actually in the segregation of the components at the front end of the process. And that's particularly prevalent in the automotive sector. So essentially, there's a hierarchy of difficulty of extraction based upon what the product is and how heavily embedded the magnet is, which I'm going to show you. So to give you an idea, I've picked 3 products across here. First one is a hard disk drive. In a hard disk drive, there are typically two sintered rare earth magnets in this voice coil assembly in here. The amount of material ranges from about 2 to 25 grams. And the problem is the material is nickel plated, it's fully magnetized, it's glued into the assembly, and it's heavily embedded. So they're typically 8 to 10 security screws holding the top on. If you move to an automotive application, quite a large majority of magnets in the automotive sector are embedded in epoxies and they're glued into the rotor. But you have to do a lot of work, which I'll show you in a second, to get the rotor out of the application. But there's quite a large amount of material in there, anywhere from sort of 0.5 kilo up to 2 kilos in the drive motor of an electric car. And then in a mobile phone, the magnets are very tiny. They're separated all over the place, and they have a range of coatings on them. And again, some of these coatings cause a problem. I'll try and cover that later. So if you think about a conventional car, it goes into a recycling plant. Then several components are manually separated: the radiator, the catalytic converter, the tires, and the battery, for example, where there's legislation to do it. And if you look at the makeup of the conventional car, about 75% of it's ferrous, and then you have a split of different metals. And then you have the combustible, non-combustible materials, the plastics and the rubber down the bottom. And once these parts have been taken off the car, then the rest of the car is treated fairly roughly. And I'm hoping this video will play. I'm going to turn the sound down in a second. So I'm hoping you can still see that and you can still see my presentation. But essentially, the rest of the car, once these components have been taken off, is typically shredded. And then beyond that stage, you have different separation techniques, so magnetic separation, electrostatics, density techniques to separate the various metal fractions, the polymers and the combustible materials. Now, the problem with a hybrid electric car is you have a much more complex and diverse range of materials in there. So if you just take the rare earths, and I've stolen this slide from Gareth Hatch, the rare earths are scattered all over the car. But if you look down here, there are about 25 plus of other motors on a vehicle. So you have the main drive motor, the generator, you have speakers in the doors, you have the you have fans over the top of the battery, you've got the power steering unit and so forth, and they're scattered all over the vehicle. So we have an issue with separating those components before it goes into the shredder. The reason for that is if you shred a magnet, a rare earth magnet, the material is extremely brittle and it breaks apart. So typically electronics and automotive scrap are both shredded. If you shred hard disk drives, the magnet material breaks apart, it's extremely brittle, and it's still magnetic, so it sticks to the other ferrous scrap. So this is a ball of shredded hard disk drives here. And it sticks to the shredder itself, and it contributes significantly to the maintenance costs of a shredder, particularly the small scale ones. Now, if you shred one of the larger sort of drive motor assemblies, and this is from Axiom Recycling, what happens is the motor assembly, the soft magnet material in the motor distorts. It can blunt the shredder tools. The permanent magnet pops out of that, and then it's basically crushed to a powder. And what happens is this powder gradually oxidizes through the shredder plant, and you find it in the fine fraction at the end. At that point, it's mixed with lots of metals. It's heavily oxidized, and the value of that is so low that you wouldn't be able to recycle that in the West. So there's a really big separation problem, particularly for the automotive sector. Just to emphasize that fact, when I was in Japan recently, there was a cutout of several generations of the Toyota Prius. What you can see here, this is the end of the engine on a hybrid car. This is the generator here. This is the drive motor. So there's a lot of work to disassemble this manually to get to the drive motor in the first place. And there's a lot of work to strip the various components out to get to the rotor here, where you can see the permanent magnets. They're then heavily bonded into that structure. They're internally mounted in amongst the soft magnet material. And I've just shown you what happens if you try and shred this. Having said that, there are some applications on the car that may be easier to get to. Power steering unit, in this case, this from the Toyota Prius. You can prise off the can at the end. The magnets are surface mounted. They're coated in a material which is easy to remove, and we can get to this material and separate it more easily. And the speakers may be similar to that as well. So there needs to be a study of all of these different applications and the manual disassembly of those components. So once you get beyond that stage in terms of recycling, the other issue you have is that the composition of magnets changes based on the application, even within one component range. So this shows you the dysprosium content, which is one of the additions to rare earth magnets. For hard disk drives, each dot is a different manufacturer, and this is by year. We did this in a project called Remnants. And you can see that the dysprosium content varies all over the place, even within one application. If you move to automotive, they tend to have much higher dysprosium ratios because it helps with the thermal stability of that material. So essentially, we need new solutions to separate, sense, and then purify and reprocess that material, which is what we've been doing in Birmingham with partners across the EU. So one of the things we've been looking at is to develop sensor lines to work out where magnets are in scrap. So in this case, this was through a company called Acrio. We built a sensor line, and they're building one for Birmingham, which is going to Tyseley. In this case, they had an optical array magnetic sensor under this conveyor system on here. What happens is it detects the magnetic field and the optical image, overlays them, and then it feeds that into a robotic stage. And then the arm will pick up the electronics, and what you see is it's just literally cropping the corner off the hard disk drive where the magnet is, like you earlier, and we can separate that component, and then it goes on to downstream processing. And we're also looking at these types of stages for loudspeaker modules and other forms of scrap. I.e., what we're trying to do is to reduce the manual labor costs. So the techno-economic study basically showed that you can reduce the cost by about 70% by introducing that robotic stage. Then what we do is we've been developing a technology called HPMS, hydrogen processing of magnet scrap. Basically, if you process these magnets in hydrogen, so this is the voice coil assembly from a hard disk drive, the magnet material breaks apart, the coating peels off the surface, it removes it from the glue, and then we can mechanically liberate this powder from the rest of the electronics. And crucially, it demagnetizes this material here, so it no longer sticks to all the ferrous components. So we've been scaling that gradually through time. This is a 300-litre reactor, which is at the university. In there, we can get 500 corners of hard disk drives. So this was real scrap coming from a recycling plant in Sweden. And what happens is you load the scrap in this drum. It's porous. We then subject the material inside to hydrogen. The magnets inside the corners break down. And then as we rotate the drum, the powder falls through this conical shaped piece and we collect it down here. And this is essentially what it looks like. So this is the magnet breaking apart. This happens in around 20 minutes. You can see the coating peeling off the surface. And then when we you'll see it in a second. This is a voice coil assembly. This is the drum rotating. All of this you wouldn't normally see because it would be in inert gas. And then in the pot there, from that particular scrap feed, we can collect about 5 kilos of powder. And then as the powder comes out, you can see there are still nickel flakes in that material. What we then do is we simply sieve that material down. We can separate bits of screw and plastics and the coating. And if you sieve it down to 90 microns, the nickel content, which started at around 5 to 10%, is around 400 ppm. Now what you have here is an alloy powder. So it's at the back end of that supply chain I started off with. And we can reprocess that material directly back into new magnets, hence reducing the cost and reducing the environmental burden. Now, one of the things I'm going to touch upon at the end of the talk is how end users can help. Well, one of the ways that you could help is to design the coating in such a way that it's ideal for our process. So if you have a nickel coating, we have to sieve it down to 90 microns, which we can do, but it takes more time because you have a finer fraction. If you developed a triple layer, which some of the pump manufacturers are now using for us, you can strip that off and it peels off into 2 to 3 millimeter pieces, and we can sieve that out very easily with the 3 millimeter sieve. So just in simply changing the coating on the magnet, it makes it easier for us to recycle it. Now, at the back, if you want to reprocess that powder back into new magnets, you have several options. You could take it all the way back to solvent extraction and chemically liberate the elements. You could recast it, which is what Lesco and Metals have been doing in the UK, or you could put the material directly back into magnet manufacture, which is what we've been doing in the group. What that looks like is you have your hydrogen reactor here, you pass the material through a milling and sieving stage, blend the powder together with new constituents, align and press the material back into a solid material, which is the same as primary production, and then sinter that material back into new magnets. Now, the reason I mentioned the composition earlier is if you look at the composition of different magnets, so in this table here we have a voice coil magnet, N42SH grade and N45, both used in the automotive industry. They have different levels of dysprosium in here. And one of the things we've been doing recently is blending these different compositions together once we've separated them as a powder and looking at whether we can predict what the properties would be like once we've reprocessed and blended those powders together. So in our case at the moment, if we take a starting magnet, measure its magnetic properties, which you can see in this graph at the top here. So this is magnetic strength and resistance to demagnetization. The green line is the starting magnet. The gray one is the recycled one. This is what we can do today. In the next step, we'll be able to push this back up to where this green line is and increase the coercivity because of the equipment we'll have. But essentially, if you start off with these different magnet grades, you have all these different properties here based on these 3 different magnets. And what we want to do is to blend them. And we have shown recently that you can predict what this coercivity value would be like by blending these different ratios together. So the composition is quite critical. Now, how the end users could help would be to buy magnets on composition and not grade. And I'll come on to that in the last few slides. So how can the circular economy be encouraged for rare earth magnets based on what I've told you before? Well, firstly, labeling of magnets would really help. And there are 2 projects in the EU that are looking at this, MaxCycle and SUSMag Pro, which I'll cover at the end. We need to provide far more information to the recyclers on products which contain magnets, where they are, and give them dismantling advice. Ideally, we should be eliminating glue or changing the binding material so it's easier to get out. We should be encouraging end users to buy magnets on composition and not grade, because at the moment, end users buy a grade of magnet and you can get to that grade with different compositions and processing routes, which gives you more variability. We need to design the product so you can get the components off a vehicle far more easily, so just the component itself, and then change the design of the component. We could do with changing the coating materials. Some are more difficult to remove. And ultimately, we'd like to see standardization for magnets, and that is being developed. There are standards coming out for that. And there is a project called SUSMag Pro, which we're in, who are developing a database to provide advice to machine designers on best practice for recycling of magnets. And I put the link in here. So I've tried to answer some of your other questions, Philippa. So what do we have in the UK? Well, we have unique IP, which we could capitalize upon. But to take that to scale requires capital investment in an immature market, which is quite challenging, and it needs support. The UK is unique in having certain parts of the supply chain, like less common metals, who can cast the rare earth alloys. We really need to integrate magnet and motor manufacturing, which I know I've talked about the APC before. And in terms of the LCA, the main barrier at the moment really for me is the lack of good quality data on the primary production to compare the recycler route to it. And in terms of legislation, at the moment, a lot of the critical materials are lost, and there's no drive or target to do this because for the automotive sector, the legislation is weight-based, and often the critical materials are a small fraction of the overall weight of the car. Just the last 2 slides, just to give you a feel, the SUSMag Pro project that I mentioned earlier has 20 partners. It's spread across the EU. And actually, a lot of what these guys are doing in the EU is based on Birmingham's technology over the last 10 years. And we're currently scaling up the processes I showed you earlier into this building, which is the plasma building on the university campus. And then eventually it's being scaled at the Tyseley Energy Park through a company where the technology, HPMS technology, is licensed, called Hypromag, which has investment from Macango Limited. And that is part of a project called RARE, and the partners are listed. So I'll stop there because I think I'm out of time.
Absolutely bang on time, Alan. Well, thank you. Really interesting, and actually it really sort of brings home the need to close that loop, session of the topic, and actually getting you guys involved early in those design phases, actually, to understand the full composition of what you really require. So we've got a question from Mike Sutton, which I'm going to ask you. What is the percentage recovery of the rare earths within your hydrogen process?
So within 5 minutes of tumbling the vessel, we'll extract 95% of the powder from an application. So it's very high. If we kept rotating the vessel, it would be even higher than that. But to give you a feel of the separation efficiency, it's about 95% in 5 minutes.
Excellent. I have a question for you, Alan.
Yeah.
I've just been thinking about some of the supply chain challenges that society might face going forward, and given the urgency and the need to move to electrification, given that a number of these critical and rare earths are used by different sectors, and the fact that there's immaturity in the sort of recycling market, do you think that there's going to be pressures in terms of meeting the demands in terms of electric vehicles because of the supply chain for these materials?
It's a difficult question to answer that. So, I mean, basically, you know, a lot of the material is coming out of China. They have large overcapacity that they could rely on. So the challenges around supply will be dependent often on what happens in China. So obviously in 2010, there was a supply restriction from China, which spooked the whole market and the price went through the roof. It's very hard to predict whether that will happen again. But given all the, it depends how you view risk, I guess. You know, if you look at what's happening politically around China, then I think we should certainly be developing our own market in this area, that's for sure.
Thank you.
In the essence of time, and there's a few more questions coming in now, but I want to make sure that we've got enough time at the end for some Q&A. So thanks, Alan, and I know that you're staying with us for the panel as well. So we'll post some of those again to you in a bit. So thanks. I'm delighted now to welcome Jackie Murray to give a presentation. Jackie is the Deputy Challenge Director for the Faraday Battery Challenge.
Okay, I'm waiting on my video, Philippa.
Okay, Catherine, can you sort out Jackie's video?
There you go. You switched it off, so I couldn't link back. Have you got my slides, or do you want me to share them?
We can share them if I'm not sure if you want to share them.
Either.
Okay, if you've got them ready to go.
That's fine. Right, let me just put them onto. Oh, move everybody out of the way. There we go. I think that is working. Is that working for you guys?
Just need it in presentation mode, Jackie, if you've not.
Apologies. Something's happening, or I've crashed the entire system.
And you need to now do the display settings at the top. You've been here, you know this.
No, that's
all right. Okay, do you want me to see? Ilana, can you share Jackie's slides, please?
I'll do an intro while you get the slides up.
Yes, sure.
So I'm Jackie Murray. I'm Deputy Challenge Director of the Faraday Battery Challenge. I'm perhaps a little unusual for a civil servant. My background actually is an extraction metallurgist. I did 10 years on the steelworks. I worked on most of them in the UK and visited a fair few others. I then went on and regulated heavy industry, power stations, steelworks and the like. So have a bit of a feel for industrial regulation and pollution control in particular, but also some of the challenges in circular economy in particular. About 3 years ago, I joined the Faraday Battery Challenge, and it's been a fantastic 3 years being on this mission, this £274 million mission from the UK government, really to join together a sort of UK team to get large-scale manufacturing and research, some of the most exciting research in batteries for electric vehicles into the UK. So if you flip on a slide, I always have been talking about for the last 3 years about why are we doing this, and it's always been through an automotive lens, a volume automotive lens. And I think if I help people understand why from a volume automotive, we can then talk just quickly on some of the major cross-section ones. So do you want to flip the slide on? So this is the main slide, and what it talks about is it shows just if you're an automotive and you're trying to get a platform, you go through the V curve and you're designing and validating your architecture and your product. And you heard Alan talking about trying to think at that point about the end of life. And actually those end of life requirements for internal combustion engines have had a sort of 120 years of development, right? So actually we're used to going and taking our car to get scrapped, and there's a whole industry around that in the UK and around the world. What's interesting right now is the pressure that car companies have been under, really to transform to electric. The graph on the right shows you the actual emissions achieved in sort of a teal colour, teal, and then the predicted regulatory requirements for an average fleet of vehicles by 2030, and you're looking at 67 grams per kilometre. Now that's for your fleet, right? So what that means is there's a huge emphasis on car companies at that point to have a large proportion of full electrics, because you have legacy cars, larger vehicles and other bits and pieces on the road. So there's this dramatic transformation required, but the decisions have been made and are being made right now for those architectures for 2030, because to get to full electric, you can't use an internal combustion engine hybrid. You've actually really got to get a large proportion of your fleet to full electric. Now, when I look at that from an, yeah, that's fine. When you look at that from an automotive point of view, you can see actually that it's been challenging in the last few years. And we know about Dieselgate, and we know about the real world test drive cycles that are now imposed. But we also know that that's driven a switch from diesel to petrol. And the bit that's not on this is really the fact that we all also seem to be obsessed with driving SUVs around our towns and cities, and they're obviously slightly heavier. So we've seen a kick up in CO2. But all of this has sort of come together to tell the automotive industry that they need to really transform. And if you click again, it'll tell you that you're looking at sort of 15 million passenger cars have to transform by 2030. And that's huge. And you're seeing the car companies trying to move through that pre-COVID, and it's going to be a really exciting time post-COVID. But we also then hear news and we have conversations with other sectors. So what we also see and hear is things like Maersk and Marine saying that by 2050 they're going to be net zero, carbon neutral. And how they're going to do that is, I don't know, but to hear big international shipping companies saying that. And actually part of that probably reflects the fact that they have had regulation since January that they've never had before in international waters, and the emission of sulfur from fuel oils that they've been burning. So they're suddenly realizing that there's regulatory systems that can be brought to bear. You've also then got mining saying net zero, and companies like Vale and Rio Tinto with big budgets looking to actually get to move to that. You've heard perhaps this week about Hitachi and Hyperdrive joining forces to look at producing battery electric hybrid trains for those parts of our network that aren't fully electric on those branch lines. I live on one, so you're hearing those industries really move. I don't know about you guys, but I'm a big Formula One fan, and listening to Formula One this weekend was a bit of a wake-up call to hear them talking about net zero in Formula One and doing that rapidly, both Mercedes and actually the chief exec of F1. And then, when you look at buses, there's all the ultra low emission zones in London and big cities, which is all around, whilst it's not around CO2 per se, it is around those emissions at the tailpipe. And so you are looking again at electric. So if you flip on, all those drivers tell you that you've got batteries being with the only realistic right now technology. Now that's not to say for buses, for marine, for others, that fuel cells aren't going to be in that. Fuel cells and batteries are complementary together. But right here, right now, for the platforms that you're making decisions on right now, you're talking huge contracts. I mean, some of them will be in the billions of pounds sort of mark. And it's companies like Toshiba and Panasonic and Samsung and Cathol who have the quality, who have the, you can do the due diligence for the liabilities and warranties that you'll need for those vehicles. So right here, right now, you can sort of predict massive growth in the battery sector. So flip on and keep going. So those graphs are hockey sticks, but actually they're a couple of years out of date, and actually they've only got bigger because of that cross section. Now, when we look at batteries for automotive, we have these targets, and these are all in the process of getting updated. But what I wanted to point out on this slide is actually the recyclability has to fall in line with those 7 other product targets that you're really trying to achieve, and the whole world is trying to achieve. So you need to have recyclability, but you can't do that at the cost of safety, for example. You can't do that at the cost of not being able to fast charge and the power density, and you can't do that at the cost of range. So how do you balance all of those targets? And it's a challenge. And Alan's point earlier is you do need this joining up, I think, to look at the whole system. So if you flip forward one more, I've stolen a slide from Philippa's colleague, Julian Hetherington, in the Advanced Propulsion Centre. And his role is looking at the supply chain and the implementation of a gigafactory project in the UK. And the reason I like this slide is, yes, I think it is one of those keystone pieces in whatever format it actually comes in. It does hold together this arch. But actually, if you look at this arch, the pieces that for batteries are missing are the bottom two on either side. And actually, really, you could almost turn those into meeting again in the middle, because, or we should be meeting them in the middle as a really good example of the circular economy. The recycling processes that Alan was talking through there, actually there's a lot of similarities with some of the comminution, and, which is the truing up of raw minerals, and some of the processing that you use to extract. And even if they're not exactly aligned, some of those recyclers that will come from recycling, they're at a grade that needs to go through further refining, and you can make them cost effective by actually pulling them through into the virgin or sort of reduction techniques. So we need to pull those together much closer, and they are the bits that are missing in batteries in particular, but actually they're some of the bits that I know we have some real strengths in the UK, and we talk about the aluminium smelter up in Lochaber on Ben Nevis, if you've not come across it, that's entirely fed by hydropower, so it's a very low carbon extraction process, or the efficient and very high-tech nickel extraction, nickel refinery down in Clydach, which is not too far from where I'm sat at the moment in South Wales. So we have some real support, real industry in there. And actually on the recycling side, we also have some phenomenally well-regulated metal refiners in that space too. So we have the raw ingredients, but we really do need this system to come together in the next couple of years. And it is some of those keystones that bring that motivation to bear. And we do see projects like British Volt that you might have seen announced recently, looking at recycling very, very particularly, not just for cost, although cost is obviously a significant part of it, not just for making sure you've got raw material supply, and that you heard Alan speak about China and some of the same challenges on refinery of nickel and cobalt and lithium, etc., with it all being done in China, exist in the battery field, but also because that we need to bring more local supply chains together, because the life cycle assessment of electric vehicles is going to become I'd like to say a differentiator, and the reason I say that is because when you look at regulations like the Eco-Design Directive out of Europe, that's the one that requires people who sell washing machines and tumble dryers and other products to put an energy rating on them. I don't know about you, but I'm slightly obsessed by buying A++ or AA+, or whatever it is that looks, it is a differentiator. It does, as a consumer, push me to making a different decision. And they've already done a preparatory study on electric vehicles and the use of the Eco-Design Directive. And what you may not know is actually they also use it to block imports of products with low ratings and high impact. So you can kind of see how this product isn't going to go down the same route as just purely transport differentiation. It will also be around its environmental credentials and its supply chain credentials. So if you flip on one more, I think I'm nearly done. So I just wanted to click through and bring up all the different things. So Faraday Battery Challenge actually is part of a bigger picture. We work with EPSRC and we work with the Advanced Propulsion Centre, but we also work alongside other industrial strategy challenges like driving the electric revolution, which is Alan is very, very core to, but also things like Made Smarter, which is all about the digitalisation of manufacturing. And we do that through 3 pillars in Faraday, with our academic base, our collaborative R&D, and our soon to be opened, hopefully this year, UK Battery Industrialisation Centre, which is a very exciting manufacturing piece. When it comes to batteries, they are almost it's a continuous process, and therefore interrupting to mess around with trials for all of you who've ever worked in continuous manufacturing is just an absolute headache for yield loss. And when the costs of these of the batteries are so high, yield loss actually has a massive impact on price of the end vehicle, and also, even if it gets too bad, whether the vehicle remains valid. So there's some really exciting stuff coming in that space very shortly. And I think that, Gloria, is possibly my last slide. If you flip on one more. No, that was my last slide. This one shouldn't really be in there. But actually, what I can sort of say on this one is really the focus in Faraday has always had recycling in there. We are aware that, like Alan, that actually the research into it is at early stages. There's some application of techniques that you can use today, such as pyrolysis and other sort of techniques, but actually making these more efficient, making them more effective, getting higher recovery rates, and also that capital infrastructure investment into the UK is really important. So at academic level, we have 10 million into the ReLib project. If you flip on one more, we've got another 10-15 million in the collaborative R&D space in recycling and reuse, and that's really about ways and techniques to improve the commercial sort of recovery levels of these. And just alongside all of that, I get to sit in a government group that we've sort of pulled together on sustainable batteries, looking at everything from the work going on around the world in life cycle assessment for batteries, looking at all the different policies and working alongside DEFRA and the BEIS product safety team, the BEIS eco design team, the DEFRA battery directive team, just to sort of try and tie up all those policies to make it easier in this space to navigate it for companies coming in. I think that's enough for me. Surely, Philippa, I'll hand back to you.
To me, thank you, Jackie, that was excellent. Certainly a lot going on there. Right, I'd now like to introduce our next speaker, Professor Francis Wall. Francis is a Professor of Applied Mineralogy at the Cambridge School of Mining at Exeter University.
Well, thank you very much for inviting me to talk this morning. And you can see I put my affiliation on this slide as University of Exeter. Should confess I am from its Camborne School of Mines, and so I'm very much a geologist stuck right at the beginning of the supply chain. So maybe I'm a little bit of an imposter then in today's end of life session. But actually, I think Jackie nearly gave my talk for me to follow on very nicely after what she said, I hope. And I made my title Winning and Winning Again. And I put here the headline message, which I hope might be something interesting for people to think and talk about, is that coming from the primary material side, we absolutely are campaigners, if you like, for recycling and looking after the material that we've gone to all the trouble to get out of the earth in the first place. So we really need a mixed economy of raw materials, with the mining at the beginning driving sustainable development. It's got to be doing good things for the communities and the countries and the companies that are doing it. And that's our first win. And then after that, we really need excellent material stewardship, including recycling absolutely as much as possible when we get to the very end of life and can't do anything else with it, to keep the materials in use. Because many of the metals, whether it's lithium or copper or neodymium that we're using in electric vehicles, they're really great sustainable materials, and they should be able to just carry on again and again. And that's my winning and winning again scenario. And I had the presence of mind to grab a screenshot, Philippa, earlier in the week when Andy Leyland was talking from Benchmark Materials on Tuesday, and that was all about supply chains. And this is Andy's very nice graph for lithium. And he produced the black line showing that actually we don't have enough lithium supplies ready to go online yet to give us all the lithium we need for the batteries that we're proposing to manufacture. And so although we need to recycle, we need to be mining too. So it's mixed economy. And sometimes we find from the primary raw materials side that when we talk, people get very enthusiastic about recycling as being the answer to everything. But in these new materials especially, we need to have the two together. And I guess that's a message from our side, is that often we find the research environment in the UK will split. The geologists and the processors and mining engineers are applying to different schemes and different research councils than the people doing recycling. And we really need to be very much joined up together, because as Jackie was already explaining, there are a lot of skills that are common to both. So we need more raw materials to be put into circulation. And so then as the geologists and mining engineers out on the front end, and people from the UK, we're really one of the biggest mining finance countries in the world, as Darren Quayle was talking about on Tuesday as well. And here's a picture exploring for rare earths out in Malawi. This is a company, Makango, who I can give a name check because Alan mentioned them too in his talk. So they're investing in recycling as well as trying to open a new rare earth mine in Malawi. Now, Malawi is one of the world's poorest countries, and so this would be fantastic. This is a big deal. It's a small project in the world of mining, but this is a real big deal for Malawi if this mine at Songwe Hill could open. And so as geologists, then we're working on that. And I'm not going to explain the detail of the slide, but we do things like geomodels, so modeling what deposits look like so we can target the ores better, and then looking at all the characteristics of the rock so we can get them out in a more efficient way, more environmentally friendly way. We look at all the people aspects around, and I think many of these techniques are also very similar ways that are being looked at from a different point of view in recycling. And so here's a picture here, staying with the rare earth theme. Here are some rare earth ores. And so it's just a rock with a pretty pink eudialyte in it, or an electric car with a direct drive motor, or a computer with a hard drive. These are all sources. And I wonder if there are more techniques that we already know from the primary raw materials that we could blend in and help people who are trying to view these ores, these new ores, are cars and computers and wind turbines, and help make that more efficient. Just a couple of differences. They have different materials in them. Alan mentioned a balance problem. In nature, it puts together the rare earths without singling out neodymium, so we always end up with more cerium and lanthanum. And talking to people about how we use those elements that will be in oversupply if we get enough neodymium for batteries is really important, so joining up with manufacturing. And then for the modern ores, they're complicated. Now, we can't help what the Earth did hundreds of millions of years ago, but why on earth can't we sort out what we're doing in manufacturing now? There's really very little excuse, in my humble geological opinion, really, for us not designing those things properly right from the start, so that the actual process mineralogy, if you like, is much, much simpler when we come to take those ores apart and recycle them. We can do something about that. We can't change geological processes from hundreds of millions of years ago. That challenge, we just have to get better at solving. And one of the other techniques that we're using now, that's a headline of today, is life cycle assessment. And certainly there's a lot more work going on now, Alan, on the characteristics of providing primary raw materials, which we can then join up with what happens when we recycle. And this is a piece of work. I can give Rob Pell a name check because I think he might be on the webinar this morning. And what we're doing here is looking at the very early stages before we've ever built a mine and looking forward so we can design to an environmental footprint. And of course, once you've got those data, we can eventually design to a whole life cycle for these materials, right from mining through manufacturing and use and recycling. And when we come to that, of course, we're going into a circular economy, and here's an Ellen MacArthur diagram. And I like this one because, see the little mine truck? Can you find that in the red circle at the top? That's, it says finite materials, and it's kind of barriered off from the nice butterfly circles that go round and round. And really, we need to join these up. We don't want to be barriered off. Because although they are finite materials, as I said, once they come into circulation, there's no reason why they can't just keep going round and round if we're clever enough with the technology and careful enough. The Earth has plenty of materials for us to use. It's the resources that we need in order to mine and keep those in use. That's what we have to watch. And joining up then between primary raw materials and recycling, the mining industry is already there in some respects, and so I'll just show an example of that. If you're looking at this and wondering why I've put a tourist coach into a talk on recycling, then if you have a look carefully, can you see that's rock around there? And this is actually 0.5 kilometre below the ground in a chromite mine in Finland. And they're mining here chromite and then taking it down the road and combining it with scrap iron to make stainless steel. And this is often called material stewardship. The mining industry started over 10 years ago looking at this, and many smelters now take recycled material. And so combining these is coming in the major metals already, and we have to get much clever at that in the specialist raw materials and the new materials coming in for electric vehicles. And so then when you're thinking as a manufacturer of components or cars about your responsible sourcing choices, there's a bit of a forest of all of these different things at the moment. Do you want to say that your material is from 100% recycled material? Do you want to say that actually you're not taking it back to raw materials at all, that you're reusing stuff as much as possible? That's the best thing to do in a circular economy, of course. Do we want secure UK extraction? That's possible, that can come, things like tin, tungsten, lithium. Do you want responsible supply from some of the big mines around the world who are really working very hard to make themselves zero carbon, as Jackie said? Or do you want to help developing countries like Malawi? Or do you want to help the marginalized artisanal miners? And I don't think there's a straight answer to that. It's very much a menu for companies to pick from and decide what your mix of your responsible sourcing choices should be. And I just wanted to end with just a plea that I hear so many times, people saying we don't want cobalt from the DRC. So I'm hopping from rare earths to cobalt now, but it's the same. We don't want rare earths from China, or we don't want cobalt from the DRC. And actually we do want cobalt from the DRC, because when you have people like these children in this Amnesty International image, their families have nothing, and they're trying to provide by getting involved in some rather dangerous and difficult mining. Sorting that out is what we really need to do so that these people have a better life. And where companies like Google, for example, with people like Actor actually going straight in there and trying to help sort out how these people are mining. And so that's another responsible potential sourcing thing for you, is how do you help people like that rather than walking away. And there's lots of things coming now with big data and blockchain and traceability. So you might think in the future, what if these people always own the material that they're mining, and it goes into our supply chain and then is recycled and just loaned out to us to use? I think with new technologies and big data and traceability things, there are some different business models altogether that people around the world could begin to think about. Thank you very much, Philippa.
Thank you, Frances, and a really uplifting note there to end on, actually, that actually taking social responsibility and having that impact could be the way to change our business model is really good. Thank you. Really interesting. Just to remind people, if you want to pose any questions and questions, not answers, but questions to our panelists, please feel free to do so at the bottom of the screen. But now to introduce our last and final panelist, Professor Emma Kendrick, who is the Chair of Energy and Materials at the University of Birmingham, School of Metallurgy and Materials. Emma.
Okay, thank you. So I'm going to be talking more about batteries and reclamation and recycling of the materials that we can reclaim from lithium-ion batteries. We heard earlier from Jackie about some of the programs that we've got in recycling here in the UK. And the first one that I just wanted to mention was this Faraday Institution funded project, which is called ReLib. This is a multi-institutional project looking at all aspects of lithium-ion battery reclamation and reuse. So similar to the Eleanor McCarthy, we try and look at it as a bit of a circular economy project where we have the battery pack, we can remove the modules, we can test those modules to see if we can reuse them for second life applications or not. We can then disassemble those modules into cells, and the cells into components, and the components back into the raw materials again. And we're interested in seeing if we can do various aspects of reuse of those materials, both within the batteries as they are, or if we need to upscale or reprocess them back into constituent materials to remanufacture, for example, back into a cathode again. So this project is coming to the first part end, which is in March next year. And we're currently going in for a 2-year renewal process where we'll be working with additional institutions as well. Secondly, I also wanted to talk very briefly about an Innovate UK Faraday Challenge project, which I'm involved with, which is called R2Lib. This is another collaborative project with several universities. WMG are very much interested in the plastic components and what to do with those plastic components. We're also working with the University of York, who's looking at the green solvent and changing over green solvents for substituting NMP, for example, for other green solvents, again with Circa. And then we have a variety of other industry partners as well, of which not all of them unfortunately have popped up here today, but we're working with Iconichem, who are turning or taking the reclaimed cathode material and turn it back into the precursor salts. PV3 are looking at remanufacturing that cathode material to be able to reuse in the cell. And we're also working with MSolve, who are developing a process for opening the cells. Now, a lot of the work that we've done to date in the UK and elsewhere has been on shredding batteries. So we put the cells modules into a shredder, they get shredded, and then we reprocess them to reclaim the materials back from that. What we wanted to do as part of this Faraday Challenge project was to see if we could obtain purer waste streams by actually disassembling the batteries first and then separating out the components. And so what you can see here is a process flow, which we've developed as part of the project, which looks at extraction of the anodes, the cathodes, the plastics separately, so that we can actually then produce pure waste streams to some of our partners for reprocessing. So, for example, Iconichem, who take the cathode material back to its constituent salts, very much would prefer a pure waste stream so that it costs them less to remanufacture the salts from that. And again, PV3, who manufacture those materials, need pure salts to then make the battery materials to go back in. So we've developed a process now where we can fully disassemble the cell. We've managed to reclaim 87% of the materials from the cell. The 20 odd percent that we haven't reclaimed is actually the electrolyte. And this is because we're using a water-based recovery method to try and limit the use of any solvents within the processes. And so this is some results that we've obtained in collaboration with Vanessa Goodship and her group at WMG. And you can see here that we're looking at not just the end of life batteries in this case, but we're also looking at QC rejects. And the processes that we're developing for the end-of-life cells also work with waste, which is produced by the cell manufacturers. And depending upon how far end of life we've gone, we can actually reclaim the current collectors pretty much whole, and we can separately reclaim the graphite material from the anodes and the NMC materials or LMO materials for the cathodes. And on the right hand side are just some micrographs of those materials that we've reclaimed. Now, although we can take the materials back to the constituent elements and then reprocess them, actually one of the things that we would like to do is actually create a short loop recycling process. So one of the things that we've done in particular is look at to see if we can actually take these reclaimed active material components that you can see here in the flakes. We've got the cathode on the left hand side there, where we've now had about 5 kilograms delivered to our partners for reprocessing, and we've reclaimed our anodes as well. And we've done some work on trying to process the anodes so that we can directly use this back in a cell again. We've also tried with the cathodes. However, because we're using a non-organic solvent approach to the reclamation of those cathode materials, we think we're getting some degradation of the oxides during that process, and it needs relithiation before we use it. However, this is not the same for the anodes. And what we've done is reclaim both the anodes from the end of life and the QC failed, and we've then processed them back directly into a battery again and tested them. And so what you can see here is some micrographs of the reclaimed graphite, and these are some voltage profiles for both QC rejected on the left-hand side cells and also the end-of-life cells, and the graphite that is reclaimed from those. And by changing our process routes that we use for the reclamation, we can actually obtain specific capacities which are very similar to what we would expect from a non-recycled cell. And what you can see is that the step 4, or the 4th process route that we've developed at the back there, you can see very similar capacities both from the QC rejected and the end of life, with a very small amount of first cycle loss associated with it. And just to highlight some of the aspects of the work and where it's going, currently we have the first demonstration of a robotic battery disassembly unit which is being constructed at Tyseley Energy Park. So some big robots have gone into place, and these are there to disassemble currently the pack into the modules. And what we'd like to do next is start looking at robotic disassembly also of the modules and cells to try and separate those out, not by hand, but by an automated and more intelligent robotic process than we've currently developed. And as part of one of the outputs of ReLib with the University of Leicester and Andy Abbott, we've developed a really fast delamination technology. We're creating a portable demonstrator, a mobile demonstrator, where we can take that to actually start looking at the reclamation of the materials from scrap around the UK at the different manufacturing sites. And so hopefully I've given you a bit of a whistle-stop tour of battery recycling. Happy to answer any questions. Thank you.
Thank you very much, Emma. That was really interesting. I'd like to invite all of the panelists back to, I would say, the floor, the virtual floor, and we're going to have some questions from the audience. So I'd like to kick off and ask Federico Patilinia to ask your question to the panelists. Maybe a question for Alan, as it's about rare earths.
Yes. Hi. Good morning, everyone. Yeah, my question was around the capacity of rare earth metals and kind of social equality, really. Is there enough rare earth from what we understand in the earth currently to supply enough perhaps advanced electric vehicles, because from what I've understand from the talks today is that electric vehicles use quite a few in various components. Is there enough rare earth to perhaps provide electric cars to the capacity that we've reached with internal combustion cars?
Yes.
Yes.
So rare earths are as abundant as tin, many of them. So it's not, although it's got rare in the name, they're not rare in the earth abundancy for the ones you want. The problem is having the processing capacity to convert that ore into a material and then into a magnet. And that's what we lack. So at the moment, world capacity is probably somewhere in the region of about 150,000 tons. We know China can double that capacity quite quickly. But it's a processing problem, not an earth abundancy problem.
Okay, thank you.
We've then got a question that I'm going to ask, which is from Richard Lillystone, but I don't believe he's going to ask it live. So it's really, I suppose maybe one for Emma and Alan about the amount of energy it takes to manufacture or produce a new battery or a new magnet versus the amount of energy it takes to then recycle and reprocess it, and what the balance is there. I don't know, Emma, if you want to go first from a battery perspective.
I think Jackie may know some of more of the specifics of the numbers than I do. One of the things I would say is that there's different aspects of the recycling process. So it's not just about taking everything back to its original constituents and remanufacturing it. There may be some benefit at looking at short loop recycling as well. So taking the components as they are and be able to use them back in the battery, because then you don't have all the costs of that manufacturing of those materials up front because it's already been done. You may just need, for example, a reconditioning step to be able to use those materials. And that is definitely uses less energy than going back right to the constituent transition metal oxides and transition metal salts to make those cathode materials, for example. Jackie?
Can you ask me the question again? Because I was looking.
Yeah, so yeah, that's fine. So it's just a question about the energy, sort of, if you like, of creating the materials in the first place, then the challenge of using the energy to recycle them and get them back to a state of use and reuse.
I think some of this goes back to some GCSE chemistry, right? So when you look at ores, they're bound with oxygen normally and other elements, but normally oxygen and things like silicon. Francis is going to give me a talk at the end of the presentation. And so my background's steel, right? So iron is bound to oxygen 7 times weaker than aluminium, for example. So you have this inherent energy requirement to break those bonds and actually get to the metal. So when you look at from a raw material processing process, you've got a high energy content. So for every ton of steel, I think the most efficient plants in the world would give you about 2.2 tons of CO2, for example. And then you have things like electric arc furnaces that will start with 100% scrap and remelt. Now they have huge energy requirements too, but they don't have to overcome those oxygen bonds. So whenever you're using a recycled material, you tend to have a massive improvement in energy demand. But you need to know what you're doing. So the steel industry started in 1876, I think, in Teesside, something like that. And so they've been making those processes more and more efficient. And that's where electric arc has come in. And there's reasons why you have both. And actually a lot of it is to do with how you can supply the market. What's important, I think, for the energy in these products is because there's a far greater scrutiny on them. I don't know how often you think about, your carbon emissions in the building of the building you're sat in right now, your house or wherever you are. But actually, when you buy an electric vehicle, there's a definite focus on it. So I'm expecting to see legislation around that for the European market at very least, but also other markets around the world.
Thank you, Jackie. Our next question is from...
Do you want me to address that for magnets, by the way?
Oh, sorry.
Just quickly, there was an LCA paper by someone called Ben Sprecher at Leiden. So he did a comparison between Chinese magnet manufacture and the route we're talking about in this presentation. Jackie just highlighted that perfectly. You basically, a lot of the energy for rare earths is in extracting the oxygen, getting to a pure metal, then casting it, and then making it into a magnet from the alloy. So bear in mind, we extract the alloy and we put it straight back in. So it's something like it's about 80%, 85% less energy is required to produce a magnet using the route I've explained today than primary.
Thanks, Alan.
Excellent, thank you. So our next question is from Emily Wardell, and as a packaging manufacturer, I'm interested to establish if corrugated, that's 100% recyclable packaging, will have a role to play in the end-of-life logistics of batteries. Maybe Jackie can answer that one.
So actually, if you have a look at the cohort of companies in the Faraday Battery Challenge, we do have dangerous goods packaging companies already in there. And actually the element they're looking at will be safety, but they're always mindful of that life cycle analysis that's going on in this space. So do I think they'll have a role to play? I think anything that reduces the environmental impact of the final products has a role to play. And it starts with, I guess, how raw materials are being mined or reprocessed and that impact, but it also includes how you transport and how you charge these products. So all of it will have a part to play. And when you look at what we're offering as funders, whether it's APC or it's the Faraday Battery Challenge, in consortia that are applying in, you are always seeing people that are mindful of actually this end of life requirements that are going to be on us. So yeah, there's some really interesting requirements. Those 8 targets that I showed probably help you frame it, because you know, you still have to meet fire and other safety requirements. You still have to make sure it's contributing to the overall performance of the end product as well.
Thanks, Jackie. Alan, I'm just wondering, you know, you mentioned that paper. Would you be able to share that link with me afterwards, and then we can get it out to the attendees from Ben? That would be really useful. I'm sure people would be interested in seeing it. I know I would be. Thank you. So now we've got a question from Sylvian Baltak.
Hello, good morning, Sylvian Baltak, Senior Consultant at Element Energy. I have a question about recycling. One of the recycling projects that you mentioned that is happening at the demonstration stage in the UK is looking at recovering plastics, among other things. And I've got a question regarding the value that recycling plastics may bring, because unlike metals, you know, plastics are much cheaper, so the money value is usually lower. So my question is this value that they bring more around reusing them for making new batteries and thus avoiding emissions from making new plastics? Where do you think that, you know, you can use plastics and resell them to other applications, maybe non batteries?
Okay, so I think that was to me.
Yeah.
Yeah. Okay. So at the moment, the plastics are generally used for creating energy, so they're burnt. Mm-hmm. And most of the recycling process is used, first of all, a pyrometallurgical and then a hydrometallurgical route to reclaim those materials. Now, we're not saying that the plastics could be used, but they could potentially be utilized as fillers in other applications, or maybe used in other fields. And certainly the laminated plastics that we use as the pouch materials, and we've got a huge issue with that from not just batteries, but from cosmetic industry and food industry. And I think it's not necessarily just a battery related question in that respect. It's actually a wider related question to what we do with those types of laminated plastics.
Can I jump in as well? I think it sort of also fits with some of the questions that have popped up around rate of recycling and the rate of production. So this isn't about the rate of production of electric vehicles or the plastic used. It's about the rate of end-of-life vehicles coming off. So you have to really put all of this into context of a market that is fed by end-of-life cars. So if you think about Nissan Leaf, there are probably only a few hundred a year of Nissan Leaf 1 coming in as a stream of vehicles into that. You also maybe have some hybrids like the Prius coming off as well, but there's not a huge number of them. You don't compare the numbers going onto the road, it's the numbers coming off the road for your business cases. So there's always this weird lag. When it comes to plastics, we do call them being burnt, but as an ex-pyrometallurgist, I'll have to say that you also get energy recovery, and you also get hydrogen, so they act as a reductant as well, which helps you get back to base metal. But it's a challenge here, and there is always going to be this lag. Plastics don't tend to make money, metals do, right? And we have got to a point where at the moment it isn't making money, but there's a definite business case. We're at a really pivotal moment for the industry. And the reason I say that is because it costs at the moment somewhere between £700 up to about £1,500, maybe a bit more, to deal with the end of life electric vehicles. Bulk of that is transport into Europe. So the UK really does have a driver for investing in infrastructure in the UK, and that's to reduce the actual cost of the cars going onto the market right now. So you have an amazing amount of things lining up. The use of plastics in this, they're relatively low energy, they're relatively low CO2 compared to losing some of those metals. And it's important that we use all of our knowledge of recycling and what we've done in the past to get the right outcome. And the UK has great regulation and legislation around that. And whilst batteries are exempt because they fall under the batteries and accumulators regulations for all you legal geeks out there, actually vehicles are subject to the end of life vehicle directive. And that's been around, I think, since about 2007. And actually that's maybe even before actually. And that's looking, that has a target of 95% of your vehicle has to be recycled. And so actually there's already very challenging targets in place for vehicles. For batteries, because that's about to be consulted on by DEFRA, that's about to get updated. At the moment it's 50% by mass. So you already have some challenges here. It's not an unknown space. It's not something people are just thinking about. It is something that we are very conscious of.
Thanks, Jackie. Not complex area. Next question is from Shanta Desai. Would you like to raise your question to the panel? No? I'll raise it.
Oh,
well,
yeah, I've managed to unmute myself. Yes.
Yeah.
So I'm Chanda Desai, and I work as a consultant for Nissan. So my question is for Jackie, the first one. Now, with the pandemic, we're seeing or we are expecting that CO2 target challenges, or that might be delayed. Although we have got the zero neutral or carbon neutral 2050, but the 2030 target might be extended. I don't know. I'm just asking the question. If that is extended, then will the drive for EV vehicles really go ahead? Because what we are seeing is the minute the government incentive drops for EV vehicles, you see a drop in sales. So where will our EV vehicles stand with no motivation from legislation drive, no government incentive, and OEMs, of course, have got a rather low profit margin for EV vehicles as compared to ICE. So where do you see as post-COVID this whole scenario?
So that's why I was talking about that transformation, right? I don't think the government is currently consulting on 2035 that no more internal combustion engines, potentially including hybrids, which is pretty controversial to the automotive industry. They're consulting on that 2035. So the pushback from industry will be that doesn't give us enough time to generate the cash from our existing models to pay for this research and development of brand new electric vehicles. Having said that, I have absolutely zero evidence that shows that this government is actually deviating from that. In fact, COP26, which will take place next November, actually I think that's going to be one of the fundamental places that the UK government's going to lobby to get everybody else on. And the reason I don't think you're seeing that fundamental shift away from that policy, even though, you know, potentially it could put certain car companies out of business, is because you're seeing people, the public, wanting to come out of COVID in a different space. Now, that's nice for me to say, and some polls and things like that have sort of, it's giving that information to government. But actually in May, the Tesla Model 3 was the biggest selling car in the UK, and the second biggest was the Renault Zoe. Now that's, I mean, they're minute proportions of the overall market, but what that's telling you is people are still buying full electric. And with the changing way we're working, I don't know about you lot, but I've only worked from home for the last 4 months. I've got 2 cars that are sat on my drive. I don't need 2 cars with this working model. And I think that's going to be massive drivers. So the rub is in the middle in terms of how car companies can transform their product range, and whether that legislation can hold without putting a significant proportion of the car automotive industry underneath. So I guess my point is I don't have the full answer, but I don't think you're going to see any appetite to withdraw from this space. But there may be some practicalities that need to happen alongside it.
Brilliant. Thank you. Thank you, Jackie. Could I go ahead asking my second question as well?
We're just trying to get a few more in the essence of time.
Okay, that's fine.
Sorry. Thank you, though. I've just got a question from Jeff Bicknell here. I'm not sure if he can, I don't think he can join us live, unfortunately, but it's how is the environmental impact of mining measured? And isn't this a factor that also needs to be considered in weighing up on mining versus recycling? Francis, I don't know if you want to.
Yes, so if you do a life cycle assessment, then you can include environmental impacts in that as well. So we normally see out of LCA some kind of headline figures about global warming potential, but actually in LCA world you can put pollutants and things into your models as well. So, and you can even put social factors in there in some varieties of LCA. So you can do it that way and have some kind of quantified and hopefully when it's all you know, a little bit more progressed, some standardized way of comparing different ones. But then there are many schemes looking at the environmental performance of mines. Many mines would use environmental management systems like ISO 14001, and then there is mine site schemes like the Initiative for Responsible Mining Assurance, and all kinds of things that customers can actually look and see what the performance of either the mine site or the company is. And if anything, I would say that this people, the mining companies and also the customers to some extent are falling over themselves to get lots of metrics in there, and what we need to come out of that is some clearer ones that are easy for people further downstream to actually see what's going on. So lots of different metrics that you can look at the moment.
Can I also jump in? You also have to weigh it up against the current product that you're using. So I was in Bolivia last year, and I used to regulate industrial sites. And so I can see best practice technologies being applied in poor countries like that, but not the full considerations that you need to have, right? So we can work with those companies and we can make sure that that happens in our supply chain, right? And things like the life cycle analysis will require us to do that. But I do always want to say to people, you know, there's this thing called oil and gas, right? That doesn't magically appear in your petrol station, right? And actually some of the environmental impacts of extracting oil and gas seem to get forgotten. You know, we've seen pictures of shale gas. We know what happened in the Gulf of Mexico with BP, Nigeria with Shell. Actually, and also the impacts of that CO2 producing fossil fuels on poor country is actually massively negative. So the work on electric vehicles is really important, and it's important because we have such scrutiny on us to make sure we don't do the same again. So yeah, it's a great question, Jeff.
Thank you very much, Jackie. We're nearing midday now, so unfortunately we have to wrap up. I'd like to thank all our speakers and panelists, Alan, Jackie, Francis and Emma. It's really been an interesting morning, and we've had some great discussions with our attendees as well. So thank you very much for coming today.
Yeah, thanks everybody, and yeah, lots of chat and additional questions that we couldn't get to, so we'll try and get some of those answered with the panelists and get those back out to you at a later date. We've got our fifth and final session tomorrow. Gloria and I are breathing a sigh of relief, and I think some of the backroom staff support as well, but it's looking at some of the best practice and actually what is the opportunity for the UK going forward, and are there particular priorities that we should be addressing. So I hope that some of you can come and join us again tomorrow. We'll be sharing the links and really appreciate it. As I said at the start, there'll be a short survey when we close this, so please, we appreciate your comments and your feedback, because it can only make sure that these become better events and more tailored to the requirements of the audience. So we really appreciate. So from me, I'd just like to stay safe. I can't say it to put my teeth back in. Stay safe and stay well, and thanks for everyone for your participation.